So good afternoon, everyone. Today we are having a speaker who is actually working here at our observatory, Piotr Kołaczek-Szymański. Piotr was graduating doing his PhD in Wrocław University, working on stellar astrophysics, and then he moved to Liège, Belgium, where he finished his first postdoc, and he moved since the beginning of this year, he moved here, and he's now part of the group of Dorota Skowron, working on also stellar astrophysics, and he's going to tell us today about some stellar mergers, right? Yes, yes, yes. So the floor is yours.
Thank you very much, Rebecca. So the story I would like to tell you today was mentioned during the last Polish Astronomical Society meeting here in Warsaw in last September. But it took only 12 minutes. So this story deserves, full 45 minutes of telling. That's why I'm standing here, and that's why I decided to tell you a little bit more about single and very unique object, which is really interesting. I hope I will, explain everything clearly and without any further doubts. So first of all, usually when we are giving scientific talk, we are following very proper and very popular way, yes, which in Polish is sometimes, down this division of spher, dzida, into przeddzidzie, śróddzidzie, and zadzidzie, of course. So we have omne trinum perfectum, 3 parts, and always the first part is the scientific context, of course. Then we have methods and calculations, and the last part are results and preferably conclusions. So usually, I mean, maybe not usually, but quite often we are stopping here on the results and conclusions are missing. But because this is a single object I'm going to tell you about, I think we will have to switch the methodology a little bit. And I would like to tell you this story in a chronological order. So it will resemble a crime storybook, something like that. We will just follow this step by step in a chronological manner. So first of all, when I was doing my first postdoc in Liège in Belgium, I came across this interesting object. So I was looking for new massive eccentric binary systems in test data, and I came across this star. It's quite, usual at the first glance. So we have 9 magnitudes here. The early P-type star, yes, quite close to main sequence. It's located at the distance of 1 kiloparsec in the direction of Canis Majoris OB1 association. And this object has strictly periodic light curve. And you can see these 2 light curves took in test sector number 7 and test sector number 33. As you may see, it's strictly periodic, really strictly. I mean, if you will face fold it, you will see that there is, substantially no change between test sectors in this light curve. So the periodicity is 0.5 days. And the question is, what kind of variability you may see here in this picture? So I asked Andrzej Brzydulski about this object because I was originally quite confused about the nature. And of course, he joked that these are aliens because it's very problematic to explain these light curves in terms of pulsations or binarity. So because the period of this variability is so short, you cannot explain it in terms of binarity, any kind of binarity. This is because we have an estimate on mass. This is an early B-type star, yes. So just playing around with very simple Kepler formulas, you can figure out that this object would be very close to the surface of the star or even inside it. That's why it was, rejected from the beginning. And the second theory was pulsations, maybe, but this light curve is, you cannot explain this kind of shape, which has many dips, which are quite narrow and sometimes resemble deep eclipses with very sharp edges. So you cannot explain it via pulsation, via any kind of pulsation, just pulsation. And then Gregor Rauch mentioned that, okay, so he knows a few objects which are called, which are always massive early type stars, and they have very unique type of magnetosphere. And this kind of magnetosphere is called a rigidly rotating. Sorry, just give me 1 second. I know how to hide it, fortunately for me. So hide float. Oh yes, super nice. And this kind of magnetospheres are called rigidly rotating centrifugal magnetospheres. So if you have an early type star, it can be as late even as early A-type stars, yes. So we are talking about intermediate mass stars even. Even if you have very delicate stellar wind, which is outflowing from the star, yes, this is kind of line-driven wind. If you have a magnetosphere, which is well organized, this is a global magnetosphere, the wind which is trying to emanate from the surface will be blocked by this magnetic field. It will be confined in the magnetosphere. And after millions of years, after 10,000 of years, the even smallest amount of matter which is trying to be repelled from the surface will accumulate in this kind of structure and form a disk or something which is disk-like structure. And depending on the viewing angle, sometimes it can obscure the disk. And because in magnetic massive stars, very often we have oblique rotators, yes? So the rotation axis does not coincide with the magnetic axis. The aspect angle is changing, yes, with the rotation phase. That's why the structure sometimes will block the light, which is coming from the photosphere, and sometimes we will see the full stellar disk. And yes, so that's the concept, okay? That's the idea, how to produce this kind of light variations. Only about 7% of massive stars have this kind of magnetosphere. So we are talking really about a very small number of objects in our galaxy. These are different examples. So if you will play around with different values of inclination angle, and beta, which is the oblique angle between the rotation axis and magnetic axis, you can see that also the shape of the light curve is changing. Yes, so we can produce very different, types of light curves. But after playing with all these variables, so we have 3 primary variables: the rotation rate, inclination angle, and beta angle between these 2 axes. We can scan all the possibilities we may have. And here you can see, if you will vary inclination angle and beta, that you can produce this kind of light curves if you're dealing with rigidly rotating centrifugal magnetism, just in your massive star. So as you may see, at maximum, we have 2 dips, which are resembling 2 eclipses. And the problem is that our case, okay, we have 1 dip here, then we have the second one, the third one, fourth one. So we have at least 4 dips. Very careful analysis will tell you that we have 5 of them, maybe even 6 of them. So that's why it's impossible to explain this light curve in this formalism. That's a problem. But also, this is the only opportunity, yes? That's the only choice we may have in case of this object. So we have to lose a little bit the assumption that we have a dipolar magnetic field, because all of these models are generated for dipole. This is a very famous example presented by Kochukov of star, which is the massive magnetic star, with strongly non-dipolar magnetic fields. So we have a lot of multipolar components, and this is the model of the magnetosphere, and that's the light curve, the test light curve of this particular star. As you may see, we have the dominant modulation, which comes from abundance spots on the surface of the star, and then we have plenty of smaller dips which are coming from this very fine structure which is present in the magnetosphere of the star. So that's the answer. Probably we are dealing even with the extreme cases, with the extreme case of very extreme cases in total. Yes, we have a magnetic star, which itself is very rare. And then in this very rare sample, we have a star which is strongly non-dipolar with many multipolar components. So that's a unique case itself. Yes, it's worth publication solely, based on this feature it possesses. So we applied for 2 DDT programs, and we were granted this time. So the first one was on salt with HRS spectrograph to study the chemical composition and spectroscopic parameter of this particular object. And we also applied for VLT Force 2 observations, 3 of them, 3 nights, to make the spectropolarimetry, a very low resolution spectropolarimetry, and try to figure out if we see over the rotational cycle changes in the mean longitudinal magnetic field. So these are the results you may see. We have a spectrum, high resolution spectrum with fit, which is shown in this with this red line. It's quite satisfactory. This is a helium-rich star. And that's also a hint towards magnetism, because almost all helium-rich magnetic massive stars are always, hosting global magnetic fields. And these are our spectropolarimetric measurements. As you may see, unfortunately, because of these errors, we don't have a clear, 5 sigma or 10 sigma detection, but at least at the level of 3 sigma, we can say that yes, this mean longitudinal magnetic field is changing over the rotational cycle. And moreover, this change, the direction of these changes is compatible with the model that Jiří calculated for this object. As you may see, the speed, the fit to the mean light curve is not very satisfactory, but probably this comes from the fact that the structure of the magnetic field is very difficult to model. So that's why we were only able to reproduce the main minimum plus 1 additional, which is around the phase 0. Okay, and that's not the end of revelations that we may came across in this object, because Andrzej Figurski, when I was studying, very carefully doing a widening procedure for this object, he discovered that after widening the signal, which is attributed to the rotational changes, there is something left around each harmonic of the rotational frequency. So that's the original frequency spectrum. Yes, we see a nice set of basic frequency and then its harmonics. After subtracting all the signals, you will see this very narrow and equally spaced maxima, which tells you that this signal is modulated. So you have 2 periodicities at least. One periodicity is attributed to rotational changes, yes, and this is visible by this set of maxima. That's quite obvious. But the second set is this. So the separation between this maxima is related to the second periodic phenomenon, which is modulating periodically a periodic light curve. I know it sounds very complicated, yes, but we have 2 periodicities here. One periodicity is periodically modified by another phenomenon. And this movie will tell you everything, I guess. So that's the animation which shows you how the shape of the light curve is varying at different phases of this longer period, which is visible after subtracting the main variability. So generally speaking, every 23 days, the light curve looks a little bit different, because these changes are exaggerated 20 times, yes? So they are much smaller. Just by looking at it with the naked eye, let us say, yes, in the phase-folded light curve, you won't notice this effect, because it's very subtle. But if you will look at the periodogram spectrum, then everything is evident. So that's the question: why we see this modulation of the light curve? It's that's the third thing which is very unusual for this object, and also for the whole class of magnetic massive stars. So we were playing around with salt spectra and digging to all the details we may find in this spectra, and we found that there are somewhere lines which are quite shallow and also quite narrow, heavily diluted, which probably come from originate from the secondary component. So we have a binary system, and the component which is orbiting our main massive magnetic star, probably, I mean, most likely is responsible for this subtle modulation of the light curve. So probably we have a star which is orbiting a magnetosphere, yes, in the center, and somehow it modifies the shape, the geometry of this magnetosphere, and that's why with the orbital cycle we see these subtle modulations. So it's very unusual because usually around massive stars, massive magnetic stars, these stars are very often found in single configuration. So this is quite odd that we have a massive magnetic star with a very close companion. The other example is Epsilon Lupi. This is the most famous one because this is the close binary system which contains two massive magnetic components. We disentangled the spectra, and this is the spectrum of the secondary component after disentangling procedure, and it fits the quite ordinary early A-type star. So we have an early A-type star which orbits the massive magnetic star in the center. And the eccentricity of this orbit is moderate, I would say, 23 days when it comes to the orbital period, and also this is the radial velocity solution. Sorry, I don't know why this line is invisible, but it's only invisible, in the projector, not here because I can see it on my screen. Okay, never mind. So we have also the minimal dynamical masses of both components. The main component is at least 8 solar masses, and the secondary is around 2 solar masses. And then when we were trying to set up the paper, so the draft was almost ready, I decided to make another quite routine check of this object, because if you have a magnetosphere which is filled with plasma trapped in the configuration, at some distance it will try to overcome the magnetic field, and this trapped matter at very high distances will try to outflow from the system, outflow from the star. So it will carry, of course, the angular momentum. Yes, and that's why all magnetic massive stars, sorry, are expected to slow down over time, the rotation. Yes, because they are just, repelling with matter. They are also repelling and losing angular momentum. And that's the classic example, the classical example. So that's the sigma Orionis E, sorry, sigma Orionis E. And that's the star with, around 9 solar masses, if I'm correct now. And this is the light curve. You have something which looks like eclipse and the second eclipse. These two eclipses, of course, in parentheses. These are due to magnetosphere and obstruction of this matter. And if you will calculate the O minus C diagram for this star, you will notice a nice parabola, which of course tells you that the star is slowing down. The spin is decreasing over time. So I made the same simple test for our object, and the result is quite the opposite. So that's very strange. That's highly unusual. But we have a magnetic star which is increasing the rotation rate instead of decreasing. And this decrease rate is quite efficient when it comes to massive magnetic star, because if you will compare this value, I mean at least the absolute value of this rate is comparable to 1 second or 0.1 second per year, yes, over years. So that's quite fast for an object like a star, as big as a star. And here the result tells you that we have a similar order of magnitude, so 0.2 seconds per year, but with the minus sign at the beginning. So this is quite fast, but the object is accelerating its rotation rate. So that's the main conclusion from this plot. Then we, of course, were trying to find out other sources in the literature, and it turned out that there are some objects which are massive, which host magnetic fields, and are also behaving in a very strange manner when it comes to O minus C trends, yes, visible in this plots. And yes, so that's a very nice review, or some kind of review made by Takahashi and Langer just 1 year ago, where you have a compilation of magnetic area type objects divided into, three types. So we have a type which seems to oscillate in O-C diagram, so some kind of non-monotonic changes. We have some objects with clearly decreasing rotation rate, and also some objects which seems to accelerate its rotation. As you may see, we only have two objects which are highly uncertain, because always, the O-C analysis, that's not an easy stuff to perform. So sometimes results are very, unclear and questionable, I would say. Yes, so the problem with O-C data is that you only have a hint towards some kind of changes, but you cannot automatically tell if these changes are intrinsic, yes, or extrinsic to the star. So maybe something is, orbiting your object, and that's why you have a light travel time effect. That's the problem with O-C. So if you would like to prove that the object is intrinsically spinning up its rotation, you have to exclude several phenomena, and this is quite difficult for every object. So first of all, you have to exclude passband effects. If you will collect and make your O-C diagram using very different passbands at different epochs, probably the shape of the light curve is slightly, depending on the wavelength. That's why if you will prepare an O-C diagram using, for instance, U filter data, and I don't know, 5 years later, Johnson's V data, probably you will produce a fake signal. Yeah, this is complete fake because the light curve depends on the effective wavelength. Of course, we have to think about changes in the magnetic field geometry. So if the geometry is changing itself, then it will affect the shape of the light curve, and then it will propagate to our O-C analysis. Fortunately for us, test photometry is super, this is super quality. So we were able to exclude this, just from the onset of our analysis. And then we also have to exclude precession of the rotation axis, because if you have an object which is in a binary system, and also you have an oblique, magnetic field, then maybe there is a very, very delicate precession of the rotation axis, and then it also may propagate the shape of the light curve. So once again, test data came to the rescue and convinced us that this is not the case. So at least three phenomena or three effects were excluded at the beginning of the analysis. But then we have a set of four phenomena, namely standing torsional Alfvén waves. I will explain this kind of phenomenon later. Okay, light travel time effect in a binary system, because of course we have a secondary component here. And then spin up as a result of tidal interactions. So if you have a secondary component in an eccentric orbit, you have this gravitational pull which is strongest near the periapse. And then you may expect that there will be some spin-orbit coupling, yes, between two bodies. That's why you always have to exclude this kind of possibility if you're analyzing O-C data for the rotating stars. And of course, upside motion, because once again, we have a binary system at least. So all three phenomena which are related to binarity are quite easy to exclude. First of all, light travel time effect. It requires the mass of the hypothetical body, which is at least 8 solar masses. So if the changes we see in the O-C diagram for this object are due to some, extra body in the system, which is very massive, and it forces our magnetic star to move around, and then we are interpreting this movement as acceleration of the rotation. It requires at least 8 solar masses. So this kind of object is, lacking in this region of the sky. So we can just proceed out. Maybe, yeah, this is, that's a possibility, but we can, I guess, all of us can agree that this is very unlikely possibility. Yes, a dormant black hole which is orbiting this body on some very extended object. Yeah, so it's unlikely. Okay. Yes. Then we have spin-orbit coupling with this horrible formula which allows you to calculate what's the rate of rotation period change exerted by the second companion. You can calculate that the secondary component should force the primary to decelerate the rotation on this level. Yes, so not accelerated but decelerate. So that's why this phenomenon was also crossed out. And we have an upside-down motion. Of course, this one is present in every binary system, but the period of this upside-down motion is around 12,000 years, so it's very long, and it cannot produce this kind of changes over 30 years of observations we have. Yeah, so the last thing we have to exclude, and the referees were very interested in forcing us to exclude this phenomenon, are standing torsional item waves. So this is my first contact with this kind of variability. They are very elusive. They are highly speculative phenomenon. I'm not an expert. I mean, I know basics of stellar oscillations, of course, but these are very special. If you have a star which is very spherically symmetric, yes, and you have some frozen magnetic field, because of course the magnetic pressure is much smaller inside the star than the gas pressure, yes. So the field is frozen in the star. You can imagine that you have an equilibrium situation, just a dipole, yes, which is aligned with the rotation axis. And then you are trying to slightly, how to say it in English, I don't know, but you are trying to slightly make a torsion of the star. Yes? So you are trying to rotate it a little bit more in some direction, release it, and try to figure out what's happening. So it will try to move to the equilibrium solution where all the magnetic fields, which are confined to the star, will come back to the original position. That's why these alpha oscillations are present only if you have a stable, well-organized magnetic field, and then something is kicking out your star from the equilibrium position, and this kind of torsions will arise at the surface of a star. So currently, I mean, till now, nobody showed that this kind of oscillations are real. So they are very speculative. The theory is only linear, without any kind of damping mechanisms, excitation, driving mechanisms. And we have this only in paper. So that's quite unfortunate that we are fighting with a theory which is not developed enough to be falsified. Yes, that's only a proposition. Now deal with it. Okay, when it comes to oscillation periods, that's an example, once again, for sigma Orionis E. Takahashi and Langer calculated these models for very different geometries of magnetic fields. And then they were calculating linear equations of motions and solving them to figure out what periods of this specific oscillations are. And that's the answer. So for different geometries of magnetic field, you may expect oscillation periods around 1 year, from 1 year to around 100 years. So that's a very long. I mean that's a really huge interval to scan. And we were trying to exclude this kind of possibility by means of analyzing the amplitude of such a wave required to produce exactly the same O minus C changes we see in the diagram. Because if you would like to make a fit to O minus C, assuming that your star is changing its rotation slightly because of distortions, you may check what's the amplitude of distortion wave. So how many cycles around the full angle you have to drag the gas element around the star to produce exactly this changes. And that's the result. So you have to at least turn around the star and deform this geometry over full 2 pi. So that's a lot, yes. That's almost unphysical. Probably below this limit, some kind of magnetic reconnection would happen, or some kind of process related to very intense, very vigorous internal mixing due to fast rotation. So that's why maybe we cannot exclude it completely, because this is not fully developed theory, yes, but we can say that this kind of oscillations are quite unlikely for this particular object. And that's why we are left with this result. So our object is the only massive magnetic star which where it was possible to prove that these changes are really intrinsic. So we have an object which is truly accelerating its rotation rate. Yeah, and then we, as a final check, run some very simple, very basic, but still also very informative simulations in one-dimensional or 1.5 dimensional MESA code. So we have a position of our object, which is highlighted here, and the color is corresponding to the normalized rate in the period of rotation. So as you may see, we have several tracks which are contracting back after the merger. They are trying to settle back on the main sequence after rejuvenation. Our object is somewhere here. This is the normal HR diagram, and this is so-called spectroscopic HR diagram. And where on the y-axis you have a quantity which relates to luminosity over mass ratio. As you may see, these results are very consistent, and they are also consistent not only when it comes to the position of these tracks, but also when it comes to the value which should be observed around this position. Yes, so our models are also predicting that if after the merger of the object, something is going back, something is trying to settle back on the main sequence, it should accelerate its rotation rate exactly with the same order of magnitude we see in this object. So that's why this is the only possible solution we see now. I mean, at least according to the current state of the literature and knowledge. Yes, that's the only thing we can propose here. Why it's so interesting? So I was following this chronological order to show you how small discovery was following the previous discovery, and now I would like to submerge this in a scientific context. So from observations, we know from at least, I think, 1 decade or 2 decades that when you will scan all sample of massive stars are this is a star which with at least 8 solar masses, let us say. Okay, so a star which will explode as a supernova. And then you will divide the sample into magnetic objects and non-magnetic objects. You will have a very strongly bimodal histogram. You have either objects which are completely lacking magnetic fields at the level of, I don't know, few gauss or tens of gauss. And then you have nothing. And at the far away side of the histogram, you have objects with typical strength of magnetic field on the order of 1 kilograms or 10 kilograms. So that's a very well-pronounced division, yes, of this object. And 7% of them are strongly magnetic. Then, if you will switch to theoretical simulations of and especially binary population synthesis, will tell you that if you will make a massive binary population synthesis for main sequence stars, you will notice that there should be hidden 8% of mergers products, some other products of binary interactions, and then 72% will be, essentially single stars or stars before any kind of binary interaction will take place. So that's why we have this very nice and very suggestive correspondence between these two numbers. Yes, we are observing around 7% of magnetic massive stars, and also from theoretical studies, we know that around 7-8% of them should be merger products currently. Residing somewhere in the area of main sequence. And over past several years, maybe 10 years, there were many studies trying to figure out how exactly the merging process on the main sequence looks like. And that's one of the most famous results from Fabian Schneider and his collaborators. This is the very famous paper from Nature, I believe. This animation, this simulation shows you how the magnetic field is strongly amplified during the dynamic phase of the merger. So the time is starting before the onset of the merger, just a couple of minutes. And the color shows you the intensity of the magnetic field. And during the dynamical phase, you have this very dramatic amplification of the magnetic field, which, by dramatic, I mean at least 10 to the power of 6, yes, when it comes to the order of magnitude. So you have a very tiny, not tiny, we have a very subtle magnetic field at the beginning, and after just a couple of days, you have magnetic field which is amplified 1 million times at least. And now the question is how this field behaves over time. Yes, because probably, most likely it decays somehow on the evolutionary time scale. But still, that's quite impressive that, via stellar mergers on the main sequence, you can produce objects with very strong, well-organized global magnetic fields. That's why the main conclusion is, if you would like to prove that, okay, these mergers are really happening in the main sequence, you have to look for massive magnetic stars. They are observational probes of these objects, yes, the aftermath of this process. Okay, and that's the diagram at the end of my presentation. What I would like to show you and discuss a little bit more in detail how the evolution of merger on the main sequence looks like. So that's the simulation from that's the sketch from the same paper by Fabian Schneider, made for tau scopy, and we are starting with this single case. So we are starting with over-contact binary system. Many of you probably knows this kind of systems as W Ursae Majoris binaries, yes, which are over-contact systems. And then because of gravitational radiation or some other effects, like for example, some von Seipel Kozai-Lidov oscillations in the triples or quadruples even, these objects in the inner system are forced to coalesce. And then the dynamical merger is happening. This object, just in a scale of days and then years, will travel up in the HR diagram to resemble a star which is very puffed up. It's bloated, yes, because of the lack of the thermal equilibrium. And then, so this stage is, it can resemble a red giant or a blue supergiant star. So you have an object which is, it's much less massive, but still it's really huge in terms of geometrical size. And then after thousands of years, it will try to regain again its thermal equilibrium and settle back on the main sequence. The hydrogen will be ignited again, and of course, the object after rejuvenation will start this journey towards the right part of the HR diagram. Okay, how about observational evidence of different stages, yes, of magnetic mergers, of mergers in general? So first of all, of course, we observe this over contact system. This is quite obvious, okay? So I'm omitting this case. Then when it comes to dynamic phase and also immediate aftermath, so we are talking about scales of months and years, these are of course luminous red novae. Yes, so that's the direct observational evidence that yes, we can observe mergers in our galaxy and generally in the universe. Then near the intermediate phase between luminous red novae, and full rejuvenation, we have a very unique example of the so-called blue ring nebula. So that's the object which cooled down a little bit after this luminous red nova phase, but still the matter which was ejected during the dynamical phase of the merger is visible as the very rare ultraviolet nebula. This nebula is visible only in the galaxy observation. So if you would like to see it, you can just go, to Aladdin, type this object and see that, okay, yes, it's really present in UV data. Very rare case where the nebula can be seen this wavelength. And of course, we have the whole sample of blue stragglers, which are fully rejuvenated objects, stably burning, hydrogen in the core, so they are well after this merger process. The problem is that till now, we didn't have object in the intermediate stage. So the object which should be traveling back to the main sequence and not, to the terminal ancient sequence. Yes? So that was the problem. How to observe this evolutionary stage, which is also very difficult to spot because of the time scale. So the typical time scale is around 1,000, 10,000 years. That's really fast. And of course, the number of massive stars in our galaxy is also limited. So we are dealing with a small number problem. Yeah, and of course, our object, so we propose in the paper that our object is the first object, which is the observational evidence that yes, truly after the merger, the product which is located there, then it travels back to the main sequence by increasing the rotation rate, because of course, if the mass loss is reduced, then you don't have any kind of process which can repel angular momentum, and that's why object by contracting it also speed up its rotation. Okay, so the last thing I would like to discuss now is the problem how to explain the current geometry of the system in the merger scenario. So let me remind you, we can all recall this. We have a system where in the center we have an 8 solar masses object or 10 solar masses object, and then on the orbit with the orbital period 23 days, we have an 8 times star. Yes, so that's quite tight and close configuration. If the merger scenario is correct, then we have to replace the central body with at least 2 objects. Yes, so we have to somehow fit there the binary system, the inner binary system, and to make this the triple system. It may seem at the first glance that it should be unstable, dynamically unstable, because of the tightness of the system. But after making simulations with very nice rebound X code, this is an N-body integrator code which can implement also general relativity effects, tidal effects, and some other effects. Yes, so we can make N-body simulations with all this stellar, astrophysical context which is encapsulated inside, run it, and check if for this configuration it is possible to stably, evolve such stars in such a system. And this panels shows you the evolution of. I'm sorry for the font size; it's really small. So that's the semi-major axis. This is the eccentricity, argument of periastron, and the periastron distance between the between the components. Sorry, and that's for the outer component. Sorry, the inner orbit, so the inner binary system, and the outer component, the tertiary component. As you may see, the situation is stable. This is a very fine structure of oscillation due to quite complicated von cycle causality of processes, but still you may sustain such a triple system, and then something happened and you can produce the merger of the central binary and make it a single object. Yeah, so this paper is currently under 4th round of review. It takes a lot of time, very long time. I mean, especially if you would like to convince 2 referees, yes, and they have some extra work for you to do, but we are keeping our fingers crossed that it will soon be published, or at least accepted, and you can place it on archive. Yeah, so the most important takeaway messages I would like to tackle here is that this object, this HD with this number, this is an extremely rare example of a magnetic massive star, which is highly non-dipolar. So we have a very complicated shape of the geometry. Yeah, and also we have a secondary component, which is the first observational example of modulated magnetism, just in such a binary system. what's interesting, the most massive magnetic stars are likely formed by mergers. And till now, there are only 4 observational candidates, not solid proofs, but candidates, but seems to support this idea. That's interesting because, I mean, even till now, we don't have any definitive example. So each of these 4 have some, problems, fallacities, some shortcomings, and it's extremely difficult to prove without any ambiguity that yes, this object formed via a merger on the main sequence. Yes, so that's why it's so important to find them, to look for them, and to prove that at least one of them is truly due to a merger on the main sequence. And HD 54740 is likely the first observational of evidence of merged objects contracting back on the main sequence. So it fills this gap between luminous red novae, which are just the immediate aftermath of the stellar mergers, and then on the other side we have fully rejuvenated objects, which are blue stars, yes, on the main sequence. So our star is located somewhere in the middle, and that's why it's so special, among other, of course, features it has. Thank you very much for your attention. If you have any questions, I will try to deal with them and to answer them quite professionally, I hope. Thank you.
Thank you very much. Thank you for a summary of these very different objects, and congratulations on your work. Any questions or comments? So, yeah.
For me, could we see the spin-up curve again, just to make sure that I understood what you're saying? We saw the spin-up curve, yes, the period.
Yes, you mean the O minus C diagram, yes?
Can you show it again?
Yes,
would you show it again?
So this one, it will be a lot of clicking, sorry, but I will try to do it fast. Oh, yeah.
So it's, am I reading it right? This is like period as a function of time?
This curve or this one?
Sorry?
Are you
Can tell me what's on the
yes,
left plot?
so on the left plot, you have the O minus C value,
Yes, right.
where, of course, observed is the moment of minimum light.
Uh-huh.
So we are scanning the moment of this deepest eclipse, let us say, yes. And then we are trying to subtract these values, I mean, these moments of time, versus ephemeris we calculated assuming that it should be totally strictly periodic, yes, without any changes in the orbit, in the rotational. So that's the difference between these two values. And that's why with over time, this difference should accumulate if you have any kind of change, both extrinsic or intrinsic, of the rotational period. Yes, so that's the trace of this change.
Right, but does it look like a parabola to you? Or?
It looks like parabola, of course. I mean, that's the first step. It's definitely not a line. Yes, so that's something else. Maybe there are also some, other, how to say, other terms, yes, in this curve. But because test observations are so precise, and this plot is the zoom only to this part of the O minus C diagram, you can see that the parabola is almost a perfect fit. I don't have residuals here, but I can assure you that they are really, really close to zero within error passages. Yes, so at least TESS can convince us that this is a parabola, and it means that the rate of this change is almost constant over this time scale. Yes.
Thank you.
Yeah.
Any more questions? No?
I have a question not directly related to the object, but to those alpha waves.
Yeah, the magnetic stuff.
Yes,
Yeah.
those ones. So my knowledge is zero on that. So I'm just curious, what would make the star to go out of the equilibrium, which you said is necessary to produce these waves? What is the period?
So there are, I mean, I'm aware of at least two processes, some build-up of small fluctuations due to rotational mixing. It's not really smooth and not really uniform across the solar surface. So if you have some small deviations from the clear symmetry, then they can build up and force a star to make this torsion a little bit. Yes, yeah. And then the question is if there is a process that can sustain it. Yes, so there will be some damping due to magnetic reconnection, due to internal mixing. So that's the question. That's why I mean this fight is very uneven between us and the referee, because this is it's called theory, but this theory is not falsifiable because you have zero, maybe except predicted periods, yes, of these waves in a very broad range, but that's the only thing. You have just periods and nothing else. So we don't have any kind of predictions from this theory about amplitudes, about how to call it, rising time in such a way. Yes? So how much time is needed to drive this kind of oscillations, if they can be excited at all. So we cannot say this. Yes. This is just a linear theory without damping and excitation times. Yeah. So this is highly speculative stuff. If someone would like to solve this problem, yeah, it's quite trendy, I would say, among massive stars community. So
I have a question about metallicity.
mhm.
This is always like either magnetosphere or metallicity is causing some problems in the modeling. And actually two aspects of that. One of that, how would metallicity of any of the objects in the system, or like this main star, let's say this magnetic star, would affect the evolution of this kind of system, and before or after the merger. And then, because it's still quite surprising for me that, okay, you said that it's not a very big number, 7% of the stars are mergers, but quite many of stars are massive and they are quite bright.
Mhm.
So there's still like some kind of big number for me, stars that should be mergers, and it's not so easy to actually track and prove if they are mergers. So my following question is if that metallicity could be any kind of tracer of being a merger.
Okay.
So this is like two sides of the questions.
I see your point, Milena. So you're talking about some kind of pollution that are there by elements because you have this merger process. To be honest, I don't know any paper which was announcing some clear signs of pollution, because this is the main sequence. So everything is quite normal when it comes to the composition and whole ratio of elements. Maybe there are some anomalies when it comes to ratio of nitrogen to oxygen because of CNO burning, yes, and changing of isotopic stuff and so on. I don't know, to be honest, but that's the only thing I can think of now. Yeah, the problem is that here we have just a hydrogen burning, so maybe you can expect some enrichment in helium, but then because of the magnetic field, the helium is also building up in the atmosphere, not in the magnetosphere, but in the atmosphere of such an object, because you have the gravitational sedimentation and levitation processes. And in the presence of magnetic field, these elements can be separated. So all magnetic massive stars, or maybe all magnetic early type stars, are expected to have abundant spots, yes, on the surface. And one of the main elements which is expected to be enhanced in the atmosphere is helium. So that's the problem. How to say if you have an enrichment in helium which is coming from hydrogen burning, or maybe this is just a cause of the helium buildup, yes, because you have a magnetic.
Yeah, so many elements.
Yeah, I guess you cannot disentangle this, easily.
Yeah. What? Okay.
No.
Any more comments, questions?
You mentioned that the obscuring material is the model is accumulated by wind. Is it possible that this is some trapped material from the merger?
It can be, of course. Yeah, it can
Because
be.
it looks like with handling here time scale also would be Why there is no
Yeah, the only problem is what are ejection velocities during the dynamical phase, yes, and also what is exactly the interplay of, what is the position of so-called alpha radius. That's the radius, that's the quantity which tells you at which distance from your object the magnetic pressure can be, you can overcome it with the pressure of a gas. So that's the position where you can expect the outflow is forming, yes, which is driving the magnetic field. I don't know exact numbers, I have to check them, of course, but yeah, I mean, in general, there is such a possibility, but I would say intuitively that it depends on the location of this alpha radius over the whole cycle of the dynamical phase of the motion, yes? How exactly it behaves with time, because you have a very strongly heated material, so it's strongly magnetized, of course, so the magnetic pressure is high, but also the temperatures are really high. So you have a strong pressure, which is thermal. I don't know which one can win this fight.
But why there is no nebula?
Because this nebula is ejected with the velocity which is around 500 kilometers per second, and after 10,000 of years, or 30,000 of years, it will just disperse in the space. So, for instance, for this object, if our estimates are correct, this merger should happen around 30,000 years ago, and after this time, at this distance, and with this, ejection velocity, which is slowing down, of course, slightly, you will have a nebula which is dispersed plus minus 45 degrees in the sky. So, I mean, it's too late, yes, to spot this one. That's why this kind of nebula, which can be seen here, I'm sorry, I have to run through my presentation once again, but this nebula is really a rare example because it's nice. I mean, it's well after the immediate aftermath of the merger, but still it's young enough to be seen because it's not dispersed in space. That's just several thousand years, yes, after the merger. And it will eventually, of course, disperse. So after 10,000 years, it won't be visible. Yeah, that's the problem with mergers, how to spot them. Because we are expecting a lot of them from binary population synthesis. I mean, literally, they should be everywhere almost, yes? But how to prove that the star which is located on the main sequence is an ordinary, single boron star instead of being a lighter product? It's extremely difficult to tell that. Unless you have some hints from open clusters, yes, or conving groups where you can spot them as blue stragglers. But blue stragglers are not always, it cannot always be measured the same. There are also some other phenomena which can go. So yeah, we have nice theory, which should be quite abundant in terms of number of measured products. But how to prove this is extremely difficult. And we have just 4 examples.
So how many would you expect, given the length of the phase?
Oh, I don't know. I don't know now in terms of numbers. But yeah, but okay, so let us make a very quick estimation. If we can observe around several thousands of relatively bright O and B spectral type stars, yes, several thousands. So around 10% should be several hundreds. So we can expect that several hundreds of relatively bright massive objects on the main sequence should be measured.
But then this phase that your object is on the relatively,
This one.
yeah, on this branch, it's just a piece of the whole path of the star.
Yes,
right?
exactly. Yeah. So you are starting here, yes. Then after 1 year, you are ending up here. After 10 or 50,000 years, you are here. And then you have millions of years of evolution. So of course, this phase is the dominant one. Yes?
So how many stragglers do we have or on that million-year phase?
The majority of them. The majority of blue stragglers are here, yes. So they are after regaining the thermal equilibrium, and they are truly back on the main sequence. Now we are just stabilizing hydrogen.
So I'm just trying to figure out if we can estimate the number of such objects that we should be able to find if it's a reasonable number.
Yeah.
Is there a scope for more or not really?
That's why we still have this kind of tension between observations and theory. Yes, because on theoretical grounds you have to experiment many of them, and on observational grounds it's really difficult to spot them and to prove that this is the measured points. Yeah.
Okay, well, if any more questions, we can do it after the seminar. Let's thank our speaker again. We don't see anything on Zoom, so see you next week. We're gonna talk about supernovae. Thank you. Thank you very much. Bardzo dziękuję.
No, bardzo też bardzo.
Ciekawe, bardzo.
Tak, mogę
Tak.